Hi, welcome to another 4AC learning video. In this video we want to look at example 4.3d, which is found in your lecture notes, topic 4, AC power. Now a small factory has a 25 kilowatt resistive load and a 40 kVA inductive load. The inductive load had a lagging power factor of 0.6. If the supply is 850 volts 50 Hz, determine the capacitive element required to raise the power factor to 0.95. Okay, let's see how we can address or answer this question. To answer this question, we start by drawing the diagram with two load S1 with power S1 and another load with power S2. That is the current coming in, IS, and this is my VS, the voltage source. They are given that the voltage source 850 volt 50 Hz, and S1 is resistive load, so you have only a P equals to 25 kilowatt. S2 is an inductive load of 40 kVA, but with a power factor of 0.6. Okay, so the first thing we need to do is to find the overall power and the angle so that we can find the overall power factor. Okay, we start by saying S1 is equals to P1 plus JQ1, but since it is only purely resistive, so only I have 25 kilowatt. J is 0. Now S2 is given as 40 kVA. The power factor is 0.6, therefore the angle is cosine inverse of 0.6. That's 53.13 degrees. So P2 will be S2 cosine theta 2, that is 40 cosine 53.13, that gives you 24 kilowatt. Q2 equals to S2 sine theta, that's 40 sine 53.13. That will give me 32 kVAr. So I can sum them up. Power power I will have P1 plus JQ1 plus P2 plus JQ2. So that's equals to 25 kilowatt plus 24 kilowatt plus J 32 kVAr. That's 49 kilowatt plus J 32 kVAr. Convert that to polar form, that's 58.52, angle of 33.1 degrees VA. Alright, so that's the overall power with an angle of 33.1. So the overall power factor is cosine 33.1 degrees. So that will give me cosine of 33.1, 0.837, 0.84 power factor. Right? So with this, we want to improve the power factor. We want to improve the power factor by introducing the capacitor, the power factor correction capacitor here, C. Okay, so how do we do that? Now, at this juncture, it is good to draw a power diagram. So the power diagram will look something like this, where P is 49 kilowatt and Q, the overall power, reactive power, is 32 kVAR. Right, but okay, and the angle is 33.1 degrees with the overall power factor, overall apparent power of 58.52 VA. Right, but we want to improve it to a power factor of FP equals to 0.95, or a new angle of cosine inverse 0.95, which means an angle of 18.19 degrees. In other words, I want a new triangle, a new force, where my Q is only so much. So to do that, I need to introduce QC to reduce the overall reactive power. So to do that, we start by saying P remains constant because it doesn't change, no change. Right, but if you look at this triangle here, and I have a new angle here now, 15.19 degrees. Tangent 18.19 degree is Q1 divided by P. So Q1 is P tangent 18.19, and P is 49 kilowatt, so 49 tangent 18.19. That will give me Q1, the new Q, of 16.1 kVAR. In other words, I want to reduce the overall Q until Q1, which means I have to introduce QC, right? That means the total Q is comprising of QC and Q1. So QC must be Q minus Q1. So QC is the original reactive power, which is 32 kVAR, minus the final one that I want, 16.1 kVAR, which means I need to introduce a QC of 15.9 kVAR, or QC is the voltage square over XC, which means that XC, the capacitive reactance, is V square over QC. Now V is the voltage applied, which is 850 volts, divided by QC, which is 15.9 kVAR. That gives me an XC. Of 45.44 ohms. But we also know Xc can be calculated using the formula 1 over omega C. Therefore, C is 1 over omega Xc, which is 1 over 2 pi 50 hertz multiplied by 45.44 ohms. That gives me a capacitance of about 70 microfarad. Alright, so that is the amount of capacitance required for the capacitor we want to put here. And finally, we want to compare the current incoming current supply before power factor correction and after power factor correction. So let's just use IT as the current before power factor correction, and it can be calculated as the S total divided by the voltage applied. So S total, we have 58.52 VA, kVA, that should be kVA, divided by the voltage applied, 850 volts. So that gives me a current of 68.85 ampere. Right, now the new power, once we introduce the capacitance, the new power, let's call this ST prime, is the square root of the power. If you look at the power triangle, is the square root of the power, and the new reactive power, that's equals to 49 kilowatt square plus Q1 is 16.1 square. So the new complex power or apparent power is 51.58 kVA. Therefore, the new current is ST prime divided by the voltage applied. So it's at 51.58 kVA divided by 850 volts, and that gives me 60.68 ampere. So by improving the power factor, the overall current dropped by 68 minus 85 minus 60.68 ampere. That's 8.17 ampere. So with the power factor improved to 0.95, the current actually dropped by 8.17 ampere. Okay, so that is the effect of improving power factor. Bye. Thank you for watching this video. I hope you learned something.